Hello and welcome to 4.3 Net Force. This homework assignment has to do with Newton's second law, but also now we're adding in problems where it's not just one force, but there'll be two or more forces. So sometimes I'll write net force like that. Sometimes it'll be like this, a sigma for sum of the forces. Remember, net force is just the sum of all the forces, and since force is a vector, sometimes we'll have to do the vector sum, like in number 3. Alright, so let's get to it. It says, find the net force in each of the following diagrams. Circle either balanced or unbalanced. So in the case of number 1, we could write like a formula, the net force is equal to 5 newtons to the left. And if we're writing that mathematically, we write negative 5 newtons plus positive 12 newtons. It's going to the right. And 12 minus 5, or 12 plus negative 5, which gives you 7 newtons. Notice it gives you a positive number. That means it's positive 7 to the right. That's the net force. So these, you could just tell by looking at them, they are unbalanced. And you could also tell because there is a net force, therefore they are unbalanced, and this box is accelerating to the right. Alright, this one, now we have 3 arrows, so let's sum them together. The net force is equal to negative 8 newtons, because that again is pointing to the left, plus negative 3 newtons, also pointing to the left, plus positive 11 newtons. I gotta take off points because I didn't write in newtons. Very important. Okay, so negative 8 plus negative 3 gives you a negative 11 plus 11. Oh, wow. Negative 11 plus 11, that's 0 newtons. So this is 0 newtons. It doesn't say on. It's a number 0 and then n for newtons. Oh, so there's no net force. Because the forces are balanced, there is 0 net force. And this object is moving with a constant velocity. Or maybe it's not moving and it has a constant velocity of 0 meters per second. Either way, the forces are balanced. Okay, number 3 is kind of tricky. You got 2 forces, but they're acting in different directions on different like axes. So there's 10 newtons to the right on the x-axis and 5 newtons down on the y-axis. We're not going to write a formula like we did in the previous two. In this case, we have to do some vector sums. So we have to find the resultant. And when we're adding vectors, we want to make sure that they're connected head to tail. Right now, these are connected tail to tail. So we have to redraw at least one of the vectors. Let's redraw the 5 Newton vector over here. So we start here. We go over and down. Our resultant vector, or in this case, the net force, is this vector here. Alright, so we have to do some Pythagorean Theorem, right? Because this is a right triangle. So the net force is equal to, we go C is equal to the square root of 10 squared plus 5 squared. At this point in the year, you should be very practiced at doing these types of geometric problems, trigonometry. And when you get that, it's 11.2. You're around 11.2 newtons. And since the net force, there is a net force here, so it's unbalanced. This thing is accelerating down and to the right. Okay, so let's see. Number 4, more straightforward, like type of equation type problems. It says how much force is required to accelerate a 5 kilogram mass at 3 meters per second squared. So they tell you the mass, they tell you the acceleration, and they're looking for the force. This is like a question from the previous homework, 4.2. It's pretty straightforward. So you just do F is equal to ma. The force is equal to the mass times the acceleration. And you should get a force of 15 newtons. Very good. Here's where it gets into the net force. Let's see. It says a force of 100 newtons east and 70 newtons west acts on an object, causing it to accelerate at 10 meters per second squared. What is the object's mass? The first step, you want to draw yourself a picture. In physics, it's always very helpful to draw yourself a picture. In this case, it's a Freebody Diagram. It's just a box with all the force vectors acting on it from the same point. In this case, we have 100 newtons acting to the east and 70 newtons west. You want to try to draw your vectors somewhat to scale so you can get an idea of what's going on. Now, just like we did in numbers 1 and 2, let's find what the net force is. It's negative 70 plus 100. Again, negative 70 because it's pointing to the left. Don't forget, forces are vectors, direction matters, and we show the direction by calling it either positive or negative. So we have 30 newtons. The net force, if you want to draw it kind of like over here, the net force is 30 newtons. It's important to note that this is not an additional force that's acting on the box. It's just the sum of these two forces. When you add these two up, you get 30 newtons to the right. Now that we know what the net force is, and we know the acceleration is also pointing to the right, it's 10 meters per second squared, we can calculate what the mass is. So the force is equal to mass times acceleration. Remember, it's always the net force, even if I don't write that symbol. It's the net force. Oops, we know what that is now. It's 30 newtons is equal to the mass times 10 meters per second squared. And the mass is 3 kilograms. So it's like a two-step problem. First you have to find the net force, and then you could use Newton's second law. Number 6. What is the acceleration of a 10 kilogram mass pushed by a 5 Newton force north, 7 Newton force north, and a 20 Newton force south? Same process. Free body diagram. We got two forces pointing north. 5 newtons and 7 newtons. Then we have a 20 Newton force south. So this is almost like number 2. Up above. So the net force is equal to 5 newtons plus 7 newtons. They're both acting up, so we call them positive. But the 20 Newton force is acting down, so we make that negative. So the net force is equal to 12 plus negative 20. The net force is equal to negative 8 newtons. So here, the 20 Newton force is winning. The net force. It's acting down, so it must be accelerating downward. And they're asking for the acceleration. Remember, the mass is 10 kilograms, so we could do Newton's second law. The acceleration is equal to the net force divided by the mass. The net force we calculated, negative 8 newtons, divided by the mass, 10 kilograms. Yes, we can make the net force negative in this equation too. That gives us a negative number, negative 0.8 meters per second squared. And remember, acceleration is also a vector, direction matters, and the negative notifies us that the acceleration is indeed also pointing downward. The acceleration and the net force are always going to be pointing in the same direction. So when you plug in the negative or positive net force, it'll give you the correct direction for the acceleration. Alright, I'm going to do this number 7, and then I'll do the back page on a separate video. So here we go. A 30 Newton force west and a 12 Newton force east are acting on an object, causing it to accelerate at a rate of 3.5 meters per second squared. What is the mass of the object, and what force should be added to bring the system into equilibrium? Again, you want to start by drawing a free body diagram, and now let's draw these forces. It's a 30 Newton force west, okay, and it's a 12 Newton force east. And it's accelerating. We could even write in, it's accelerating at 3.5. Oh, actually, what direction do you think it's going to accelerate? We could do a calculation, but looking at our free body diagram, it's got to be accelerating to the left at 3.5 meters per second squared. Okay. Now, it's asking for the mass of the object. We want to try to use Newton's second law, but first we have to know what the net force is. There's two forces acting here, so let's figure out what the net force is first. Negative 30 plus 12. The net force should give you 18 in the negative direction. newtons. Okay, now that we know what the net force is, we could use Newton's second law. Negative 18 is equal to, we're looking for the mass, times 3.5 meters per second squared. So you do negative 18 divided by 3.5, and you get negative 5.1 kilograms, if you round it. Okay, very good. So that's for part A. For part B, they're saying what force should be added to bring the system into equilibrium. A couple different ways you could think about this. For me, I like to think of it in terms of, okay, where's the net force? Net force, negative 18 newtons in this direction. I want to bring it into equilibrium, so I want to balance this guy out. Then the equilibrium must be brought on by making a positive 18 Newton force to the right. Now this thing is balanced out. So what force should be added to bring the system into equilibrium? 18 newtons east. Okay, very good. I'm going to break this video up now, and I'll see you in the next one.